So I have the pleasure of introducing the first keynote of the day. Abhradeep Thakurta is going to be speaking. So Abhradeep, can you pull up your slides while I introduce you? Thank you. So Abhradeep is a staff research scientist here at Google Research on the BRAIN team. His research lies in the intersection of data privacy and machine learning. He specifically focuses on demonstrating that it's possible to design differentially private learning algorithms that can scale to industrial workloads, and that'll be a lot of what this talk is about. And before Google, Abhradeep was a faculty at UC Santa Cruz, and before that, he was a research scientist at Apple and Yahoo Labs. He received his Ph.D. from the Pennsylvania State University in 2013 and did postdocs at Stanford University and Microsoft Research. So with that, Abhradeep, please take it away.
Thank you. Yeah, so today I'm going to talk to you about federated learning with formal user level differential privacy. The parenthesization over federated is to emphasize that the algorithms what I will be talking about would also be useful / applicable in the centralized training setting. And the word formal is to emphasize that the system designs what we will discuss will faithfully follow the algorithm design to ensure DP. And this work, or the conglomeration of the works which I'll be talking about, will represent the work of many folks whom I will introduce during the course of the talk. And yeah, so the first few slides will be mostly boilerplate slides just to set the stage. So we consider the setup where the data set and the algorithm lies within the trust boundary, and whatever that goes out of the algorithm is only visible to the adversary. Now, this data set can be centralized or distributed depending on the setup. The privacy guarantee will follow throughout the talk is differential privacy. The most important thing here is that we'll be protecting user level privacy, meaning that all the contributions by a single user during the course of the algorithm is protected. Third, this requires no introduction to this audience, but still, we are operating the cross-device federated setting where devices make local updates, and then these are coordinated by a centralized server / entity. And the whole process is within the trust boundary for this talk. And what the adversary sees are the models that gets deployed onto the devices. So here comes the punchline of the talk. We deployed the next-word user prediction model for Spanish language Gboard users with epsilon of 8.9 and delta of 10 to the power of -10 user level differential privacy, which equivalently corresponds to 0.1810 concentrated differential privacy. To our knowledge, this is the first time there has been an industrial deployment of a DP learning algorithm with a provable privacy guarantee. And as a side note, the algorithms what I'll be talking in this, telling in this talk will satisfy zero concentrated differential privacy, which we know is a stronger variant of privacy than just epsilon delta DP. That's just a side note. So what is this talk going to be about? In the first part, we'll start with DP stochastic gradient descent, which by now has been the de facto standard for training ML models. In the second part of the talk, I'll talk about differentially private follow the regularized leader. This is an algorithm we developed over the last couple of years. And hopefully in this presentation, we'll see some new variants or new exposition to the algorithm. In the third part, we'll be talking about the production deployment on Gboard. In the fourth part, we'll look at DP-FTRL and how it performs on empirically on benchmark data sets. So that's the plan for the talk. Okay, going to the background. So DP-SGD and its close cousin. So what is DP-SGD? You have a data set. And essentially what happens is that at every time step, you sample a mini batch of size k uniformly at random. You clip the gradients in that mini batch and average. And let's call that GT, that average object. You add some noise, mostly Gaussian noise, and then you do state update as if you were running a regular SGD algorithm, and the process continues. One thing to notice here is that the scale of the noise is 1 over k, where k is the batch size, meaning that if you were to do a gradient descent with full gradient descent instead of a mini batch of size k, your noise would scale as 1 over n, where n is the complete data set size. Here, L is the clipping norm. Sigma is the noise multiplier, which essentially depends only on the privacy parameters and nothing else. Okay. So what is the one of the main reasons behind the success of DP-SGD is this tool called privacy amplification by sampling. It says that for the same level of privacy, one can add noise as if the gradients are computed over the complete data set as opposed to a mini batch. Remember, in the previous slide, when we calculated the gradients, we added noise in the order of 1 over k, where k is the mini batch size. What this privacy amplification by sampling tool says that you can still operate over mini batches of size k, but you can pretend that the noise is added in the scale of 1 over n, where n is the complete data set size. So you can get away with adding much lesser noise. Now, what does that translate empirically? We see that for CFAR10, when you consider amplification, privacy amplification, the privacy utility trade-off becomes significantly better than when you don't have privacy amplification. So keeping that in mind, let's talk about one of the close cousin of DP-SGD is DP-Fed averaging. Here, the idea is that you uniformly sample devices, you compute per device gradients, clip the gradients, and add noise exactly as if you had done in DP-SGD, and the process continues. Instead of uniformly sampling devices, the devices can Poisson sample themselves and select themselves. Whatever I will be telling here does not depend too much on the sampling strategy. The key requirement is that you require privacy amplification by sampling to get good results. However, it becomes practically infeasible to do this kind of sampling in FL training, and I will be telling in the next couple of slides why it becomes infeasible in the context of FL. First, the client availability is limited, non-overlapping, and most of the communications are initiated by the clients. Second, to make it even harder, the size of the active population varies over time. That's shown by this picture, and it's very hard to kind of know what is the size of the active population at any point of time. And furthermore, if we introduce randomness in the process of client participation, it becomes almost incompatible with custom load balancing techniques like phase steering. So we did design a feasible protocol in 2020, but it required complex infrastructure changes, and also the amplification would have depended on the large number of available devices. So that kind of made us thinking that can we avoid this whole idea of amplification or sampling by privacy amplification by sampling altogether, because it did not seem anything fundamental to the problem. So just to kind of emphasize again why privacy amplification becomes important when you do SGD style algorithms. So the privacy utility trade-offs can be substantially worse than DP-Fed averaging if you don't consider amplification, and that's shown in the graph on the right for Stack Overflow. So again, the question is, can we avoid sampling and achieve similar privacy utility trade-offs? So with that question, we'll go to our the main algorithm for the talk, which is DP-FTRL. So to start with, DP-FTRL or DP follow the regularized leader will start with the non-private variant of the problem and will slowly build on the algorithm. Okay. So let's take the SGD, non-projected, so you're not projecting. If you take SGD and unroll the recursion, you will see that the update at time step t+1 depends only on the sum of the gradients, which are denoted by GIs, up until time t. So every update of SGD can be written as a prefix sum of gradients. So to succinctly write this, theta t+1 is essentially some theta 0 is the initial model minus some learning rate times the sum of the gradients you have seen so far. Well, an algorithm which has been there for 2010 called follow the regularized leader, also known as dual averaging, what it does is the model at time step t+1 is a minimizer of the inner product of the gradients what you have seen so far with the model and a regularizing term. It is not hard to see that this object is exactly equivalent to SGD when you treat the initial model theta 0 to be 0. So FTRL in the setup what I am writing are equivalent to the SGD update. Okay. So this will be the starting point of our designing of the DP-FTRL algorithm. the main object to keep in mind is that we want to compute the prefix sum of the gradients, and that seems to be the most important thing in the design of the algorithm. Okay. So FTRL update we discussed is a minimizer of the inner product of the gradient with the model and a regularizing term. So pictorially, you have the gradients G1 till G4, and you are computing the prefix sums. And to privatize the FTRL algorithm, to make it differentially private, all we need to compute is all the prefix sums with differential privacy. So that's the building block, the private building block we need for designing the DP-FTRL algorithm. So we'll take a slight detour into designing good algorithms for prefix sums with DP. So what you have a stream of adaptively chosen data vectors. In the case of FTRL or SGD, the gradients. And the important part is adaptive. So G2 can depend on the output that is given by the algorithm when operating on G1. G3 can depend on the output given by the algorithm on G1 and G2. And this is typically true in gradient descent or FTRL because the next model depends on the gradients and the models what you have seen so far. So you're given a stream of adaptively chosen data vector. And warm-up approach could be you add IID noise to each of the updates. So if you step back and think, this is exactly DP-SGD. So you add noise to the first gradient. When you see the second gradient, you add noise. When you see the third gradient, you add noise. And fourth gradient, you add noise. So this is exactly DP-SGD. Now, if we just consider the total noise that gets added to the final sum, that is G1 plus G2 plus G3 plus G4, if you take DP-SGD without amplification, your scale of the noise would be in the order of square root of n over epsilon, where n is the number of gradients you have summed up. Now I'm pushing the parameter delta under the rug, and also for this particular object, I'm treating epsilon to be less than 1. Now, if you consider amplification into the context, then you can get an error of order 1 over epsilon. So this, again, theoretically emphasizes why amplification is important in the context of DP-SGD. Earlier, we saw in plots, the privacy utility trade-off gets improved. Now, this one says quantitatively why it is important. But remember that we want to get away from amplification. So that brings to the more defined version of doing prefix sum computation. So let's pretend that we want to write this prefix sum computation in the form of a matrix vector product. And for the purpose of this part, also think that G1 till Gn are one-dimensional objects. We can extend to d-dimensional objects, but for presentation, it's much easier to treat each of the gradient or the data vectors to be one-dimensional objects. So with that simplification, your prefix sum can be written as succinctly as a inner product between a matrix and a gradient vector G, where the matrix A is a lower triangular matrix with all ones, and the data vector G has the elements G1 till Gn. This should be obvious that if I do this matrix vector multiplication, I would get all the prefix sums. Now we go into the matrix factorization view of computing prefix sum. You have a matrix A, you have this vector G. Now we want to factorize the matrix A into B times C, such that when you multiply C times G, C is the right-hand side of the factorization, and add noise, that should satisfy differential privacy, in particular zero-concentrated differential privacy, even when this vector G is chosen adaptively, because ultimately we want to run for FTRL cell algorithm, so we need adaptivity. Furthermore, the error, which I did the calculation here, maybe a bit clunky, but let's see if we go through it. So you're adding noise to C times G, then you're multiplying with B. So that's the outcome. And the true result is A times G. So if you do the simplification, essentially the error comes out to be B times the noise. Okay, now why did we care about the L2 norm of the noise? Well, this is governed by the analysis of FTRL, which I'm not going to get into the details. But the objective is that we want to ensure that this object B times noise is minimized. Okay, and That's how we want to factorize these matrices, matrix A into B times C. So you want privacy in the context of C times G plus noise should satisfy differential privacy. And at the same time, we want utility, that is the L2 norm of B times the noise is minimized. So that's how we want to factorize the matrix A. Okay. So first we prove a theorem. What we show is that if the noise is Gaussian, then in the continuous release model, what I mean by that is that at every time step you're outputting something, which in the context of SGD, you can think that I'm outputting a model or the gradient case output. Any row ZCTP algorithm which is non-adaptively private is also adaptively row ZCTP private. So what we say is that as long as you can design good factorization algorithm, ignoring adaptivity of the gradient vector, this vector G, we don't need to care about adaptivity because adaptivity is automatically taken care of. Why do we need to do this? Well, it turns out that it allows us to operate with arbitrary C's, arbitrary matrix C, which does not need special structure, for example, lower triangular. So with this theorem in place, let's look at a few candidate factorizations. The first one is the classic binary tree mechanism, where you have a binary tree over this vector G. The leaf node corresponds to the individual gradients, and the inner nodes corresponds to the sum of all the gradients in the subtree of this binary tree. And it is not hard to see that given if I can output this tree, I can compute the prefix sums what I want to compute based on the tree. And more importantly, any single node in that, any single leaf node in the tree only affects the nodes from itself to the root of the tree, which is order of log n. Now, this algorithm has been there for quite some time. Now, if I look at if I kind of represent in the factorization version, so the B and the C matrices would look like the one what I've shown. It is not important to actually kind of look closely at it, but trust me that you can do it in this particular form. Okay. Another factorization mechanism could be this FFT-based factorization, where you take the matrix A and factorize into B and C such that the matrix sigma in the, let's start with the matrix C. The matrix sigma is essentially the Fourier transform of the step function, and F is the DFT matrix over endpoints, and F star is the inverse DFT. Now, why can I factorize particular this way? This goes to a classic theorem from linear algebra, which says that any circulant matrix is decomposable in the Fourier basis, and essentially the prefix of matrix is a two-place matrix. So we can write in a circulant version, and we can decompose in the Fourier basis. So this is one type of candidate factorization. If you write the error due to the noise carefully based on the Fourier components, you can see that the error is in the order of 1. Okay. So another candidate factorization, which will be the crux of the talk, is the optimal factorization, where you essentially optimize the SDP over the A matrix, with the A matrix and X being the X being the matrix that takes the C matrix and computes C transpose C, and you are optimizing over the trace of A transpose A times X inverse, where C is represented as square root of X transpose. The important part here is that you put a constraint which is necessary to ensure privacy, that the diagonal entries of X is upper bounded by 1. So it's a very succinct way. It's a very succinct way of writing the optimization problem. And there are other near optimal factorizations exist from very recent papers, as recent as like this year, and I think it will be published in SODA 23 from Helsinki et al. Okay, so these are the candidate factorization. Now the question is, why do we really care about these factorizations? So first, if we look at the error from different algorithms, we see that the binary tree style factorizations actually have a much higher squared error than the optimal factorization what we have. Optimal factorization what we have. And yeah, and the more important part also to see is that the error in the binary tree is correlated at dyadic intervals, and this is because of the tree structure. Okay. Additionally, this generation of the factorization and implementation has varying costs. You have to generate these factorizations and also have to implement it, and they have varying costs. And based on that, one could choose different factorization schemes. Okay. So going back to the DP-FTRL algorithm, you don't have any sampling requirement. You compute the next batch of devices, compute the gradients. Instead of doing noise addition, what you drop in replacement of the matrix factorization algorithm, whatever is your best choices, and do the state update with the standard FTRL state update. Okay. Now, this exposition is a mix of like 3 works from 2021, news 2022, and a recent work which will be up on archive pretty soon. Okay. After having talked about DP-FTRL and introduced it, let me go to production deployment of Gboard. So this is the production deployment, and just to set the timeline, it was in early this year. We were still developing the matrix factorization algorithms. So the algorithm that got deployed is a variant of the binary tree mechanism, which we have discussed in earlier. So we use the DP-FTRL with the binary tree mechanism to train a 1.3 million parameter RNN model. This was used for next word prediction for Spanish language Gboard users. The training ran for 2K rounds over 6 days, and 6.5K devices participated per round. The devices were configured to make sure that they participate at most once in every 24 hours to ensure that we can properly bound the sensitivity or get user level privacy. The privacy accounting was a fairly involved one where you had to operate over multipass DP-FTRL with reasonably complicated dynamic program to compute the privacy accounting. And there are codes available publicly for how we did it. Now, the punchline is that to our knowledge, this is the first production neural network trained directly on user data, which has been announced with the formal DP guarantee. And this is not just federated, it's just, to our knowledge, is the first neural net trained this way. So the training satisfied user level DP of 0.81 ZCTP for well-behaved clients. What do we mean by well-behaved? The clients which faithfully followed the algorithm, including the participation limits. The important part is the clients which are not behaving well, misbehaved clients, did not adversely affect the privacy guarantee of the well-behaved clients. The model quality improved over the previous DP Fed averaging algorithm, which was the added bonus. Although incomparable, just to put this thing in context, US Census uses a ZCTP guarantee of 2.56. So just to put this 0.81 number in context. So this was our production deployment. And this is an acknowledgement to all the people involved in this multi-year effort to make DP-FTRL get launched. Okay, so now going to the fourth part of the talk, which is evaluating DP-FTRL on benchmark datasets. So here we'll be talking about DP-FTRL with multi-pop training. What I mean by that is that we'll consider the fixed dataset, and we'll say that the training proceeds in epochs. A single user participates in a fixed position in each of the epoch, and we know exactly where it participates. So the exposition what I'm giving here is for centralized model training with a fixed dataset. This techniques would extend to federated setting as long as we know the participation pattern. Okay. So first thing is that I have to bound the sensitivity of DP-FTRL under multiple participation. Let's say in the C matrix, a person participates at this red, yellow, green, and blue points. And let's call this submatrix to be C pi. The sensitivity of C, assuming the gradients are one-dimensional, it's just easier to write that way. It is max over all such participation, max over a vector U, which is plus minus 1 in k dimensions, which is the number of participations, the L2 norm of C times U, C pi times U. So this is the sensitivity of the matrix C. It might take a bit of time to parse, but if you work the math out, it's not hard to see that this is actually the sensitivity bound. Now, I told you that this is for one-dimensional gradients. It turns out that it requires non-trivial analysis to extend it to d-dimensional participation, which I will not get into the details. I will refer to the paper when it comes up online to see like why it gets tricky to deal with d-dimensional participation. And the good part is that the matrix factorization algorithm will explicitly incorporate the sensitivity constraint in the optimal factorization of A. Okay. Now, going to the empirical evaluation, the first thing is on running on CIFAR 10 with 20 epochs. So you have a batch size of 500, number of optimization steps we have fixed to 2000, and number of epochs comes up to be 20. And here I will introduce a concept called stamping. Essentially means that I will run the factorization algorithm for n steps and I will restart, ensuring that the total number of steps is 2000. So looking at it pictorially on the right hand side, after every n step I restart the algorithm. So I run a prefix sum, some version of prefix sum algorithm on every n steps and I restart the algorithm. Okay, and that's what I mean by stamping. Now, if I go to the result for CIFAR 10, the first thing to notice is that of DP-SGD with amplification. That's the purple line. The green line is the binary tree mechanism, where I'm using n, which is the number of rounds which I run the algorithm for the binary tree algorithm, and then I restart 10 times to ensure that I do 2000 steps. We see that the binary tree algorithm, the green one, crosses the DP-SGD at somewhere between 8 and 10. So actually, it can outperform DP-SGD with amplification, even the basic version of DP-FTRL. Then we go on to the FFT version. We see that the point of the inflection between DP-SGD and FFT actually shifts to the left. It's somewhere between 2 and 4. The interesting thing is that once you go to the optimal factorization, this gap even becomes more stark, and we actually move almost to the left. Okay, I will take the questions after the list. Okay. Yeah. So now the point is that we have gotten an algorithm which does not use amplification, but actually can outperform DP-SGD even at smaller epsilons. Okay. Now, going to language modeling questions on Stack Overflow. This is a standard benchmark data set for next word prediction. So here SGTM means stochastic gradient descent with momentum. So the 2018 paper was the starting point, and we started making improvement. And if you look at DP-SGDM, which is DP-SGD with momentum, reached an accuracy of somewhere between 23 and 24. And if you look at the matrix factorization approach today, what we have with 6 epochs, it closes 94% of the gap between the non-private and the private. Of course, you can think that, okay, if I run the full gradient descent version of the algorithm, it is comparable to matrix factorization, but the matrix factorization requires 340 times less compute than DP-SGD. So this is this slide actually highlights like how the progress was made over the years to reach to the point what we are with DP-FTRL. Now this is the end, almost the end of the talk. I told you about DP-SGD, then I introduced the DP-FTRL algorithm in the context of matrix factorization, gave you some insights into the production deployment on Gboard, and some evaluation and benchmark data sets. Just to end with some concluding remarks. So this is the first production deployment of DP learning with provable user level DP guarantee to our knowledge. Matrix factorization based DP-FTRL can completely avoid privacy amplification and still outperform DP-SGD. Some of the open questions, one theoretical question is DP-FTRL sufficient? It's an online learning algorithm, so the natural question is it sufficient to obtain optimal population risk for convex losses? The second question is both theoretical and empirical. Can we design efficient, possibly streaming approaches for generating these optimal factorizations, where I can avoid some of the computation costs? And the last slide is just as a pretty picture and for people to decipher what is going on. And here I stop. Questions?
Thanks, Abhradeep. I think we have time for one question, and hopefully you can answer the rest in chat. Yeah. John asks, FedAtom performs very well in the federated setting. How would DP-FTRL and DP-Atom kind of compare? You know, is the benefit of Atom overcoming kind of the benefit of DP-FTRL in some sense?
It is, yeah, it's a good question. To the best of my knowledge, if I understand DP-ADAM versus DP-SGD, I don't think DP-ADAM, I mean, it has a convergence faster, but it does not, at least to my knowledge, the things which I've seen, it does not get to a better accuracy than DP-SGD. So it converges to a same accuracy at a faster rate, but it does not outperform DP-SGD for the accuracy. And here we are comparing the accuracy. So in some sense, the advantage of DP-FTRL still remains.
Great. Thanks, Abhradeep.